All right, so this is the last of these lessons reviewing factoring. And like all the last few lessons, I'm hoping the core ideas sound familiar and that I'm refreshing your memory, not teaching you things from scratch. The last lesson is looking at some sort of special cases when factoring, and one is a difference of squares that we see a lot. And a difference of squares in general is anytime you have two perfect squares, in this case a squared and b squared. But again, sometimes it's not so obvious if one of these is a perfect square, and you're finding the difference of them. Difference means subtraction. And anytime you have two terms that are both perfect squares and you're subtracting them, it's always the same as factors in this form. A minus b times a plus b. Always, 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 always. And notice, if you look back, we FOIL this out. A times a is a squared. A times b is positive ab. But the very next step you probably do is minus b times a, which is minus ab. And those just cancel each other out. And the last thing you'd probably do is minus b times positive b, which is minus b squared. And so it doesn't really matter what these a's and b's are. If it's in this form, you'll always have these two terms canceling each other out, which means when you look at the polynomial, you just see two terms. And so the key is noticing that you have a difference of squares. And like I said, sometimes it's not so obvious if these two terms really are both perfect squares. So let's look at these examples. I'll look at these one at a time. I got 4 here, as you can see. So, for example, 9x squared is a perfect square, same as 3x times 3x. And 16 is a perfect square, same as 4 times 4. So as soon as I notice that, then I can factor this immediately. Because I know I'm going to have two factors. One's going to be addition, one's going to be subtraction in the middle. Other than that, they're all going to be the same. The first term, and the order does matter, has to be the same thing that multiplies to make 9x squared, which is 3x. And the second term has to be the same thing that multiplies to make 16, which in this case is 4. The reason the order matters, for example, if you write this second term as 4 minus 3x, or if you write them both the other way around, 4 plus 3x and 4 minus 3x, this term's okay, but here's the problem. Because 4 minus 3x and 3x minus 4 are similar to one another, but they're not the same. The order you subtract matters. You get the wrong sign otherwise. So just pay attention to the order. 9x squared came first, so 3x was first in each of my factors. That's it. And again, if you're not sure, you can go back and FOIL it up. And so looking over here, hopefully it's nice and quick. 25 is a perfect square. 4x squared is a perfect square. And so my two factors must be 1 plus 1 minus, 5 plus 2x, and 5 minus 2x. Again, really, really quick, if you notice that you have perfect squares. If you don't notice you have perfect squares, for example, if you don't notice that and you just look at this, there's nothing else you can really do. There is no GCF. It's only two terms. You can't like factor it like when you have 3 terms. So it seems like there's nothing you can do. So we either notice it and it's quick, or we don't notice it and we're stuck. Let's look at this one right here. Again, both of these, 16x squared and 9y squared, are perfect squares. And so I can immediately factor this. I'm going to have 4x as the first term in both and 3y as the second term in both. Oh, one of these should be minus. I'll make that minus. There we go. And again, so much of this in terms of recognizing if something's a perfect square comes back to, again, our understanding our multiplication tables. And if we don't know quickly that 16 is the same as 4 times 4, we get bogged down by these things. Lastly, these are powers of 4, but powers of 4 could be perfect squares. For example, x squared times x squared is x to the power of 4. Y squared times y squared is y to the power of 4. So this is a difference of squares. And it looks like this. X to the power of 2 minus y to the power of 2. X to the power of 2 plus y to the power of 2. However, we're not done. Because right here, we have another difference of squares. In fact, if you look at what I've underlined in orange, it's virtually identical to what we started with up in our notes. Instead of a and b, I have x and y. And so that means x squared minus y squared, I can factor even more. And so this is x minus y and x plus y. However, what I see underlined in red, I can't go any further. That is a sum of squares if you want to give it a name, but it doesn't matter. You can't factor that anymore. So I'll just write it down. Now, if you look at that and go, why can't I factor that more? Or if you think, well, shouldn't that be x plus y times x plus y? Well, no, because if you FOIL this out, you get x times x, which is x squared. You get x times y, which is xy. You get y times x, which is another xy. And then y times y is y squared. And notice we have an xy plus another xy is 2xy. And I don't see that right here, which means these are not the factors. But that leads us into the next part, which is what we call, when we do have factors like that, when we do have a perfect square, when we do have the same factor twice, and we call that a perfect square trinomial. And perfect square trinomials are always in this form where there's 3 terms. And the first term is a perfect square, the last term is a perfect square, the middle term is the tricky part. The middle term may be positive or negative, and it's 2 times. Not a squared, b squared, a and b. This is a perfect example that's hard to explain by looking at it like this, so I'll just write out what the factors would look like, but really, it's when we kind of use it this should make more sense. And so just keep in mind, if this is a positive sign right here, then both these will be positive. If this is a negative sign right here, subtraction, then both these will be negative, but they're the same. So I can also write this as just a plus or minus b all squared. But again, it's that middle term that's the tricky part. However, I did bring this up a few days ago in one of our lessons on the videos. I commented when we're looking at it, when we're multiplying this way, that we can actually speed this up. And I mentioned that the middle term is always the same as this times 2. And that's exactly what you're seeing here, a times b times 2. So hopefully this looks familiar beyond just from grade 10. Either way, as usual, the best way of learning this is to try it. And so let's look at these. I think I have 4 to look at in total. Okay, so these, first of all, I'm just telling you that all of these are perfect squares. Okay, and I'll show you how we can prove it, but once we know this is a perfect square, this is really easy to factor because I know it must be the same factor twice. And I know whatever goes here has to be the same, it has to be something times itself to make x squared, it has to be an x. And whatever goes here has to be something times itself to make 9, so it has to be a 3. And I know this, I see there's a plus sign right there, so I know this has to be a plus. I'm done. However, what if I didn't know for sure if this was a perfect square? Like what if, again, everything I did was so fast because I knew, because I told you, that what I have here is a perfect square trinomial. But what if you didn't know that? Well, again, the first term is a perfect square, the last term is a perfect square. It's that middle term that makes it hard to tell. And that'll be, I'll say more about that in a bit because that's kind of like the last problem from these notes is looking more at that. So for the time being, just for all 4 of these, if you're not sure how to, if you're not sure how to determine on your own if these really are perfect squares, we'll get to there in a moment. But right now, just trust me, everything here is a perfect square, which means all these have factors that are just the same thing twice, which is pleasant. It makes things simpler. And so for the one on the left, which is almost identical to the first one, the only difference is I have minus 6x here, which means it's going to be the exact same factors as before. It's going to be x minus 3 all squared. And if you look at these together, that's the only difference between them. And similar for below. If I look down here, once we know these are perfect squares, then I know this must equal something times itself. I know the first term must multiply by itself to make 4x squared. That means it has to be 2x. I know the last term has to multiply by itself to make 9, so it has to be 3. However, I don't know if it's positive 3 or negative 3, because even negative 3 times negative 3 makes positive 9. And this is where I look at that middle term. I see there's a minus there, so I know this is minus. Done. So once I know this is a perfect square, man, that was fast. Way faster than multiplying this times this together or breaking up the middle term. Way, way, way faster, because I knew this was a perfect square. And similarly, this last one is the exact same setup, just I'm adding the middle term. So I can see quickly, it's going to be the exact same factors as before. But now I'm adding in the middle instead of subtracting. And this leads me to the last question, and perhaps the most important question, which is how can we determine if something really is a perfect square without me just telling you? Well, if I look right here, there are a total of 9 different polynomials. And as it says, I only want to factor the polynomials that are perfect squares. Otherwise, I'm going to leave it blank or ignore it. All right, so For example, I'll just do the first one. If this is a perfect square, I want to factor it. If it's not, I'm going to not do anything more. So how can I tell? Well, it looks promising at first. A squared is a perfect square. That's the same as a times a. 16 is a perfect square. That's promising. Same as 4 times 4. But this is where I know it's not. Because it's not 16, it's minus 16. And I don't care if I have minus 4 or plus 4. It has to be the same thing. And a positive times a positive is a positive. And a negative times a negative is still a positive. And so I can see, because there's a negative right here, this cannot be a perfect square. There is no way I can have x minus 4 squared or x plus 4 squared and it's going to equal that. So I'm done. This is not a perfect square. Let me look at this one. Is this a perfect square? Well, again, it looks promising at first. 4b squared is the same as 2b times 2b. And 1, positive 1, is the same as 1 times 1. So now I have to start paying attention to the middle term. So I do see there's a minus here. So if this is a perfect square, that has to be a minus there. But how do I know that middle term is correct? How do I know that really is how do I know this is a perfect square? Well, let's see. That middle term, minus 4b, should be the same as 2b times negative 1, which is negative 2b, all times 2. Negative 2b times 2 is negative 4b. That's exactly what I see right there. And only now do I know with certainty that this really is a perfect square. So now I'm done. I erased that work there, but I want to keep my answer. Now I know I factored this properly. But again, if that was, let's say, an 8 right here, and everything else was the same, then this would be wrong. Because this would, that middle term, this would not actually be a perfect square in the end. So again, the hardest part is determining, really, I think at this point, is this trinomial a perfect square? And it's that middle term that is the most complex part. The first term and the last term are rather straightforward. All right, looking at the rest. This one I know right away cannot be a perfect square. How do I know? It's only 2 terms. Perfect squares will always have 3 terms. Always, always, always a perfect square trinomial. If you really have the same factor, 2-term factor times itself, there'll always be that middle term. And again, the middle term is always this times 2. So nothing more to think about there. Let's look at this one. Looks promising because I have a 16 and a 16d squared at the end. So again, I'm not going to assume this is I'm going to assume this is a perfect square, but I'm going to be willing to make changes if it's not. So if it is a perfect square, my first will be a 4 plus 4d. The 4 because it's 16 there, 4d because 4d times 4d is 16d squared, and a plus because I see a positive there. But that's it. If this is correct, let's check that middle term. That middle term of 32d should be the same as this times 2. 4 times positive 4d is 16d times 2 is 32d. So I know this is correct. I know this really was a perfect square, and so I know these are my factors. Let's look at this one. Same idea. Looks promising, okay, because those are definitely perfect squares. So 1 minus 8e. So again, if this is a perfect square, it has to be in this form. And again, the minus in the middle because I'm subtracting 16e in the middle. But is that 16 correct? Let's see. It should be the same as 1 times negative 8e, which is negative 8e, times 2, which is negative 16e, which is exactly what I have there. So I know I'm good. So that really was a perfect square in the end. All right, let's look at this one. Is this a perfect square? Well, it looks promising at first, and then no. 6 is not a perfect square. 3 times 3 is 9, not 6. And so, not a perfect square. Nothing more to do with that one. Let's get to the last row. All right, so again, is this a perfect square? G squared is, and 100 is. So, looks good at the start. I have G, and I have 10. And I'm adding here, so if this is a perfect square, it'll be G plus 10 all squared. And hopefully now we've done several examples, you can see, yep, this is a perfect square because I can quickly see that G times 10 times 2 is 20G, and that's what I see right there. And so the whole point, before we get to the last two, is just that if we can notice things are perfect squares, we can factor these really, really quickly, especially like some of these last examples. Like these ones here are kind of weirder looking polynomials, but once I knew they were perfect squares, I got from here to here really, really, really quickly. I didn't have to do any more work than what you see here. Second last one. Looks promising again. 49h squared is a perfect square. Positive 1 is a perfect square. So let me get this thing set up. So if it is a perfect square, it'll be 7h and negative 1. And let's just make sure now that we have the right middle term here. Okay, because that middle term with that negative 14 should be the same as 7h times negative 1, which is negative 7h times 2. Yep, that works. So finally, here's the last one. Is this a perfect square? Again, looks promising. I squared is a perfect square. 9 is a perfect square. So if this is a perfect square, it's going to be I plus 3 all squared. Again, that plus because there's a plus here. But let's make sure, again, this is only correct if the I squared plus 9I plus 9 really is a perfect square. And so if it is, let's see. That middle term should be the same as I times 3, which is 3I times 2, which is 6I, not 9I, which means this here is actually not a perfect square trinomial, which means maybe it can factor, but the factors are not going to be 2 of the identical factor, which means I'm going to erase all this and just cross it out because now I know this is not a perfect square. So notice before I end this, keep in mind, although we looked at 2 things today, differences of squares and perfect squares, in my opinion, and probably your opinion, difference of squares are more straightforward to figure out than a perfect square. But we see perfect squares a lot. And so the more we are used to them, the more we can speed ourselves up with rather mundane stuff. Honestly, all this polynomial work we've done the last few days, I find quite boring. It's incredibly important, but it's not interesting. It's just a process. And we have to do it a lot, so we want to become proficient with it. And quite often it helps to notice these things, because then we don't have to get bogged down by these menial factoring steps. And that's it for factoring. There's nothing new to learn about factoring, but we'll now be using it a lot throughout this whole course.